Hello, I'm Simon Pratt, and I'm presenting the convex hull of points on a sphere as a spanner. This is in collaboration with Jit Bose and Michiel Smid at Carleton University, and this is for the Canadian Conference on Computational Geometry in 2014. So first of all, I assume some knowledge of graphs and geometry. If any of this is unknown to you, I suggest that you pause this video and go look those things up on Wikipedia. That's graphs and basic geometry ideas like the distance between points, line segments, etc. So first of all, what is a Euclidean spanner? So we talk about the convex hull points on a sphere as a spanner. What do we mean by that? So first of all, we're talking about a graph, specifically a geometric graph, where the vertices of the graph are points and the edges of the graph are line segments between points. And so we say that such a graph has a path length, where a path is a sequence of edges. It has a path length equal to the sum total of the lengths of the edges on that path. And we say that such a graph is a Euclidean spanner when for any 2 points there always exists a path of at most some constant factor times the distance between those points. So the path goes through the graph, but the distance, the line segment that is from the start point to the end segment, the end point, isn't necessarily in the graph. And so what you should think about this is the path through the graph, so not going in a straight line between these 2 points, is at most some constant factor, which we call t, times the distance between its endpoints. So we say that such a graph is a Euclidean spanner if we can prove that. In 1987, Dobkin et al. Proved that the Delaunay triangulation of points in the plane is a spanner, and I'll get into exactly what that means shortly. And in their paper, they noted that Raghavan suggested that their result was a special case of the convex hull of points on a sphere also being a spanner. So we ended up proving this, and we used this fact that if you take a set of points in 3D and you take the convex hull of those points, the convex hull is, so you have these points, imagine putting a plane against one of these points and then rotating it all the way around the set of points, and every time that plane touches three points such that all of the points are on one side of that plane, it adds a face, so it adds three edges. We assume that no more than three vertices are on such a plane at any one time if you're doing this. But anyway, so if you do that, but then because the points are on a sphere that we're talking about, take all of those line segments added by the convex hull and replace them by arcs going across the surface of the sphere, you end up with something called the spherical Delaunay, specifically the spherical Delaunay triangulation. And so what that means is, so in a regular, like in the plane, if you have a set of points in 2D, the spherical Delaunay triangulation is whenever three points can be drawn, whenever a circle can be drawn on 3 points, such that no points are within that circle, the spherical Delaunay adds a triangle on those points. So it adds 3 edges, one edge between each pair of points. The spherical Delaunay triangulation is perfectly analogous. So you have 3 points on the surface of the sphere. Anytime you can draw a circle on those 3 points, specifically a circle on the surface of the sphere defines a spherical cap, defines a region of the sphere bounded by a circle. So anytime you can draw such a spherical cap on whose boundary lies 3 points, and which contains no points in your set, then you add a circular triangle, so you add arcs between each pair of points. And so what we did was we proved that the spherical Delaunay triangulation is a spherical spanner. So what that means is very similar to Euclidean spanner. So we have points on the surface of the sphere and edges which are arcs, direct arcs between those points along the surface of the sphere. So we say that such a graph is a spherical spanner if for any 2 points there always exists a path through the graph, so through edges of the graph, that is at most some constant factor t times the direct arc distance between the endpoints on that path. And so it may not be obvious, but if we prove that the spherical Delaunay triangulation is a spanner, because going from the spherical Delaunay triangulation to the convex hull of points on the sphere is just straightening out these arcs into direct line segments through the sphere. If we prove that the spherical Delaunay triangulation is a spanner, then we've proven that the convex hull is also a spanner. And it turns out that so by doing so, we reduce all of the lengths. So a direct arc between 2 points has some distance, and by straightening it out, we reduce it. And so all of those lengths change, including both the distances through the graph, but also the distance between the 2 endpoints. And so what happens if we prove that the spherical Delaunay triangulation is a t-spanner, then the convex hull of points on the sphere is a pi over 2 times t spanner. So first of all, given this set of points on the surface of the sphere, how do we construct a path through edges of the spherical Delaunay triangulation? So what we do is we draw what's called the Voronoi diagram. And so what this is a spherical Voronoi diagram, to be precise. What this means is that for every point in your graph, you draw a boundary wherever such a boundary is equidistant between 2 points in your point set, and you have a vertex wherever 3 or more points are equidistant. And so what you end up with are these boundaries that separate regions on the surface of the sphere that are closest to one particular point in your point set. So the next step is to draw the direct arc between the 2 points between which you want to construct this path. And then, each time that direct arc crosses into a new Voronoi region, you add the corresponding Delaunay triangulation edge, spherical Delaunay triangulation edge. Now, it's maybe not obvious, but the Voronoi diagram is actually the dual of the spherical Delaunay triangulation. So what that means is that basically whenever you have a vertex, a point where several boundaries meet in the Voronoi diagram, you have the center of a circle in the spherical Delaunay triangulation. You have the center of one of those circles on which 3 points are co-circular, which defines a triangle. And so what that means is that whenever 2 points have boundaries which are adjacent in the Voronoi diagram, that means that they share an edge in the spherical Delaunay triangulation. So whenever we have the direct arc crossing from one Voronoi region into another, we know that there exists an edge through the spherical Delaunay triangulation between the points that correspond to those Voronoi regions. So we keep adding these arcs, and we end up with a path between any arbitrary beginning and end point in the graph. So now the next step is we've proven that we can construct paths. So at the very least, we don't have an infinite spanning ratio, which is what happens when there may exist 2 points between which you can't construct a path in your graph. We know that we can, so we need to analyze them and determine what's the spanning ratio on this spanner. And so to do this, just out of convenience, say that whatever A and B you choose, we rotate the sphere such that A and B are on the equator, and A is to the left of B, or A is west of B, however you want to think about it. We're going to draw it such that A is to the left of B on these slides. And so from that, we can deconstruct any path into a series of subpaths of two types. The first type is where all of the, it's a maximal sequence of edges, of vertices in our path, such that all of the vertices are on or above the equator, which is along the direct arc between A and B. So type 1 subpaths, all of their vertices are on or above the equator, or symmetrically they're all on or below the equator. It doesn't matter for the analysis. We just assume that they're all above. And then there are type 2 subpaths, where the beginning and end of the subpath, the beginning and end vertices are on one side of the equator, and all the other vertices on the subpath, of which there must be at least one, which are between the beginning and end, are on the other side of the equator. So this proof is following the original proof, Dobkin's original proof, that the regular Delaunay triangulation is a spanner. And so he called these two types of paths one-sided paths and two-sided paths. And so this type 2 is a two-sided subpath because it starts on one side and it goes to the other side and then comes back. So first of all, it's useful to define some spherical caps that will come in handy in bounding both types of these subpaths. So what we do is we draw the direct arc between our beginning and end points on the path. And every time we follow an edge, that means there are 2 points, and that the direct arc intersected with a Voronoi boundary. What we do is we use that intersection point as the center of a circle on which lie 2 points on our path, 2 adjacent points on our path connected by a spherical edge, by direct arc. And we use that circle to define a spherical cap. Now, it turns out that we can prove by induction that if you union together all of these spherical caps, you have one spherical cap per pair of points in our path. If you union together all of these spherical caps, you get some region on the surface of the sphere. And then you just take their upper boundaries, so beginning with your first point on the path and ending with your last point on the path. If you union together their boundary, you're unioning together circles on the surface of the sphere, we can bound that upper boundary by pi/2 times the distance between your endpoints. And so that's going to come in immediately useful when we look at type 1 subpaths. It should be fairly clear that our subpath begins with BI and ends with BJ, and it follows those what look like straight lines in this diagram from circle to circle. That path along those arcs is upper bounded by these the union of those boundaries of the circles that we've created, that we've defined. And so that upper boundary is bounded by pi/2 times the distance between those endpoints. And so we have a nice bound on type 1 subpaths. So now we need to consider type 2 subpaths, which begin and end on one side of the equator and immediately go to the other one. All points in between them are on the other side of the equator. So some of these are not very wide with respect to their height. Just intuitively, they go a long distance across the equator, go a short distance on the other side of the equator, and then go a long distance back across the equator. And so we define height in this case to be the distance between the lowest point on that boundary between on that boundary of spherical caps between the beginning point on your subpath and the end point on your subpath. The lowest point meaning the closest point on that boundary to the equator. So the distance from that closest point to the equator is the height. And then if we draw a direct arc down from each endpoint to the equator, the shortest such direct arc gives us new points on the equator. If we measure the distance along the surface of the sphere between those points, that gives us the width. And so we want to establish a nice bound on type 2 subpaths that are not very wide with respect to their height, but these subpaths spend a lot of time jumping across the equator. That is not very good, so we'd like to avoid that if at all possible. So what we do is we construct a shortcut, just as Dobkin did in his paper. So what we do is we consider the set of points that are between the beginning and end points on our subpath and also above the equator. And we take the spherical convex hull on those points. And what that means is in a three-dimensional setting, to take the convex hull, you rotate a plane all the way around your set of points until it's created a face all the way around it, like deflating a balloon around those points. What we want to do is take the lower spherical convex hull of these points, and what that means is you take, let's say, your leftmost point, you draw a great circle that goes all the way around your sphere that it intersects that point, and then you rotate that counterclockwise until it hits another point, and then you fix it at that next point, and then you continue rotating it until it hits another point, and then another point, and another point, until it hits the last point on the subpath, at which point you have some lower hull on that set of points. But those points don't necessarily share edges on the spherical Delaunay triangulation, so what you do is between each pair of points on the lower spherical convex hull, you run this routing algorithm again. And it turns out that any such output will be one-sided, and so will be bounded by each subpath between 2 points on the convex hull will be bounded by a circle like this. And if you add all of those up, it turns out that they're all bounded by a circle like this. So any such shortcut path is bounded by pi over 2 times the distance between the endpoints on your subpath. So, good. Now what remains are wide type 2 subpaths. So type 2 subpaths that go a long distance on the other side of the equator, which we can't nicely build a shortcut for. We really need to follow this unless we come up with a better routing algorithm. But the way we bounded this was assume that instead of going along this path, what we did was from the beginning point on our subpath, we go directly down to the equator in the shortest such arc, and then we continue down until we hit that spherical cap again. We follow the direct arc in that way, and then we follow along the boundary of our spherical caps until we reach the point which is directly across from the end point on our subpath. So what we end up with is the actual path through the graph is this red sequence of arcs, and what we're going to bound is the blue curve that is on this slide, and it should be clear that the blue curve is an upper bound on the length of the blue curve is an upper bound on the length of the path, the red path. But now we need to establish an upper bound on the blue curve. And so how we do this is we first consider the distance that we travel across the equator, which is from the start point down to the equator. We will split this into two distances. Specifically, we'll draw a line or an arc or a great circle, a circle really, that goes around our sphere that runs parallel to the equator and is on the point on our boundary which is closest to the equator, which we'll call Q. And so this splits that distance from bi to bi prime being the point closest on the equator to the point bi. It splits this into the distance from bi to ai, which is the intersection between this line, this arc that we've created, and the parallel along Q, and then the distance from ai to bi prime. And so it should be clear that the distance from ai to bi prime is exactly the same distance as the height. And since we have 4 of those segments on our path, and the upper bound on following this type 2 subpath, I mentioned it in the slide, but I didn't talk about it earlier, was that we follow the subpath if the height is at most width over 4. So we know that 4 of these heights are equal to the width at most. So we can bound it by the width. Now we just need to bound the distance from bi to ai, which we do first along the boundary and then back to ai. And so since we have 4 of those types of distances, we have 2 paths along the boundary which are symmetric, and then 2 paths along the equator which are equal to the width. And so if you add all of these things together, so first of all we can bound that distance along the boundary, of which we have 3, 2 for these sections of arcs, and 1 for the path that we followed in the beginning. We can bound each of those by pi over 2 times the distance times the width of our subpath. And so what that means is that the entire curve that we've defined is at most 3 times pi over 2 plus 1 times the distance between the start and end point on our subpath. And so